Have you ever truly grasped the size of our galaxy? It's a number so vast it ceases to feel real, dissolving into mere astronomical jargon. We talk about light years, but what does that distance actually look like to a traveler? Imagine setting out from our solar system, aiming for the opposite edge of the Milky Way, not just the journey to the next star, but the crossing of the entire galactic disk. This is not a science fiction fantasy. It's a genuine question about physics, speed, and the sheer scale of the cosmos we inhabit. What kind of speeds are even possible? How does time itself bend and stretch across such unimaginable distances? We're going to step away from the abstract diagrams and put some context to the cosmic roadmap. If the pursuit of understanding these immense scales aligns with your curiosity, gently tapping that like button and subscribing helps bring these explorations to more curious minds. Settle in. Let's calculate the true cost of crossing the Milky Way. The Milky Way, the galaxy we call home, represents the largest structure we typically consider on a personal scale. It is far more than the hazy glow we sometimes observe in the night sky. It is a collection encompassing hundreds of billions of stars, massive clouds of gas and dust, and structures so vast that attempts to describe them often sound like exaggeration. To cross this system would be an effort comparable to trying to measure the volume of an ocean one drop at a time. The fundamental question remains: exactly how long would that journey take? To begin, we must establish the distance of the crossing. The Milky Way is shaped like a flat, rotating disk with a central, bulging core and long, spiral arms extending outward. From one edge of this disk to the opposite, the total span is estimated to be around 100,000 light years. While different observational methods yield figures that vary slightly, sometimes stretching closer to 120,000 light years or trimming back to 90,000, this variation itself illustrates the challenge. We are attempting to map the entire forest while standing deep beneath the trees. Cosmic dust clouds obscure our view, making precise distance measurements on this scale extremely difficult. However, we will rely on the standard, often cited figure of 100,000 light years. This figure gives us our absolute starting point. What does 100,000 light years actually represent? It means that if you could somehow ride a beam of pure light traveling at the cosmic speed limit of roughly 300,000 kilometers per second, it would still require 100,000 years to traverse the galaxy from one edge to the other. This fact is immense. The fastest entity in the universe takes a time span 1,000 times longer than all of recorded human history just to cross our home galaxy. Every civilization, every war, every invention, all of it fits within a small fraction of that total timescale. Of course, objects with mass, such as spacecraft, cannot achieve the speed of light due to the constraints of physics. The question then shifts from absolutes to the potential of our technology and our future aspirations. Consider the Parker Solar Probe, the fastest object humanity has ever launched, which achieves speeds of up to 700,000 kilometers per hour as it slingshots around the Sunday. Even at that staggering pace, a journey across the galaxy would consume over 600 million years. During that time, you would witness entire continents shift, mountains rise and fall, and ecosystems vanish and reappear. Yet, the journey would still be far from finished. This stark contrast between the galaxy's immensity and the slowness of our machines is profoundly humbling. It clarifies that discussing crossing the Milky Way is currently confined to the realm of thought experiments and theoretical possibilities, rather than practical travel plans. However, this only makes the question more compelling, forcing us to stretch our understanding of the universe's scales of time and distance. Imagine looking out the viewport of a theoretical starship. Ahead lies the vast sprawl of stars, each a sun, many with their own planetary systems. Crossing the galaxy would involve passing near countless billions of these, each with its own story and possibilities. The fundamental calculation remains: how long? At what speed? We begin with our benchmark, 100,000 years, the clean figure for a photon making the trip. We then slow this down into the reality of human-made spacecraft. The Voyager 1 probe, launched in 1977 and still traveling through interstellar space, moves at about 61,000 kilometers per hour. At that speed, the required time to cross the galaxy stretches to more than 1.5 billion years. To grasp this number, the planet Earth itself is only about 4.5 billion years old. Voyager 1 would need approximately 1/3 of our planet's entire age just to travel from one galactic edge to the other. While Voyager 1 was never intended for this mission, it serves as a powerful reminder of the gap between our ambitions and the scale of the cosmos. If we shift from actual probes to imagined starships, the numbers can be improved. Suppose we could achieve a sustained speed of 1/10 the speed of light, an enormous leap beyond current technology, but within the realm of theoretical physics. Even at this velocity, the crossing would still require 1 million years. If we could reach 1/2 the speed of light, the journey shrinks to 200,000 years. These times are still orders of magnitude longer than the lifespan of any civilization known to history. This is where the inquiry moves from technology to profound perspective. Asking how long it would take to cross the galaxy requires us to admit that no individual human could ever complete the trip. It would necessitate generations upon generations, whole societies living out their lives aboard a starship, never reaching the goal, only knowing that their descendants might. This journey would stop being a means to an end and instead become a way of life, with the galaxy transforming from something to be traversed into something to be lived within. All the while, the stars around us continue to shine. The Milky Way is an active, dynamic place. In the time required for a single crossing, the galaxy itself would have changed dramatically. Stars would be born and die in supernovae. Constellations would shift their appearance beyond recognition, and the overall map of the sky would be new. The question of crossing is not merely about travel, it is about time. To cross the galaxy is to live through epochs, watching history unfold on a cosmic scale usually reserved for geology and evolution. As we hold that realization, we can understand that the journey may be less about reaching the other side and more about fully grasping the scale of the place we already inhabit. Our galaxy is vast, far beyond any crossing we can achieve, yet we orbit within it every day. We are already participants in its motion, carried along whether we notice it or not. When we consider the time needed to cross a galaxy, the primary obstacle is the distance itself. We can easily imagine fast ships, but we must first clearly understand the road ahead. The Milky Way is consistently described as being about 100,000 light-years across. This figure, though often repeated, is complicated by the fact that we live inside it, surrounded by gas and dust, making precise measurement a constant challenge. Astronomers piece together this map over decades, using various methods, which is why the figure can occasionally stretch toward 120,000 or shrink toward 90,000. Still, 100,000 light years is the practical figure used to capture the immense scale. To truly understand what that means, we must clarify the light year. It is a unit of distance, not time. 1 light year is the distance light travels in a single year, nearly 10 trillion kilometers. When we say the galaxy is 100,000 light years wide, we are talking about a distance of approximately 1 billion trillion kilometers. This figure is so immense, it resists human comprehension. We can try to build comparisons. If the Earth were shrunk to the size of a marble, the Sun would be another marble, about 15 meters away. On that same scale, the nearest star system, Alpha Centauri, would be thousands of kilometers distant. The entire galaxy would stretch across distances far larger still, impossible to hold in a single picture. Our minds are simply not built to grasp numbers this large in any intuitive way. The Milky Way is a structure composed of hundreds of billions of stars spread across an expanse so large that even light requires 100 millennia to move from one side to the other. And this only accounts for the main disk. The surrounding halo of stars and dark matter extends much farther, possibly 2 or 3 times as wide, pushing the crossing distance into even more intimidating ranges. When we look up on a clear night, the hazy band of the Milky Way is a view into the densely packed heart of the galactic disk, where the billions of stars blur together into brightness. That glowing arc is our first clue to the galaxy's immensity. We live on a small planet, orbiting an ordinary star, about 2/3 of the way from the galactic center to the outer edge. The galactic center itself is approximately 27,000 light years away. This means that the light reaching our eyes today left the center during the last great ice age on Earth, long before recorded history. We are always looking into the deep past when we look into space. The question of distance is therefore also a matter of time. To cross the galaxy would be not only to move through space, but to traverse history itself. It is a journey measured not only in kilometers, but in centuries and millennia stacked upon each other. And yet, for all its size, the Milky Way is still only one among billions of galaxies in the observable universe. The Andromeda Galaxy, our nearest large neighbor, is located more than 2 million light years away, dwarfing the 100,000 light years of our home. In this grander context, the Milky Way is statistically average, but to us, bound to one planet and one star system, its scale is everything. Asking how long it would take to cross it is a fundamentally human question, a way of trying to bring the incomprehensible into our frame of reference. We want to measure it and put it into terms that connect to our lives. This is why astronomers so often return to carefully chosen metaphors and analogies. Without them, the numbers remain sterile lists of digits on a page. With them, we can begin to sense what these distances mean. We can say that if you drove a car at highway speed nonstop, it would take you longer than the age of the universe to cross the galaxy. These comparisons are imperfect, but they help bring the enormity down to scales where the human mind can play. Distance is more than just a challenge to travel. It is the fundamental context that dictates what kind of journey is possible. The fact that light requires 100,000 years to traverse our galaxy establishes the ultimate frame for every other calculation. It defines what is possible, what is impossible, and what will forever remain in the realm of pure imagination. It forcefully reminds us that the stars we observe are not neighbors in any conventional sense. Even the very closest ones are separated by chasms so immense that our fastest probes would need tens of thousands of years just to reach them. Yet, the question persists. How long would it take to cross? Now that we have fully established the overwhelming nature of the distance, we can begin to consider speed. How fast can we realistically go? How does that velocity measure up against the size of the challenge we face? What happens when we push against the known limits of physics or dare to dream of technologies that might allow us to bend the cosmic rules? Before diving into speed, it is worth pausing once more to let the sheer scale of the distance truly resonate. A galaxy is not a single, definable place, but an expanse so large that the concept of a single journey across it feels inherently resistant to reality. In that immense vastness, we are small, yet we are certainly not lost. We possess the unique ability to ask these questions, to measure the cosmos, to imagine impossible distances, and to share the wonder of it all. That distance may be physically beyond us, yet it is also ours because we live entirely within its boundaries. Every breath we take is drawn within the Milky Way. Every sunrise and sunset occurs beneath its canopy. We may never successfully cross it, but we are always an indelible part of it. And that realization, in its own quiet way, is sufficient to keep the thought of the crossing powerfully alive. When people visualize the galaxy we inhabit, most picture the familiar, hazy band of stars that stretches across the night sky. That pale strip of light serves as our first essential hint of the larger structure we are a part of. Though to our eyes it appears flat and cloud-like, the Milky Way is not a random smear in the heavens. It is a massive, highly organized system with a distinct shape, formed over billions of years by the persistent pull of gravity shaping stars, gas, and dust. Understanding the shape of our home is the essential starting point for imagining what it would mean to cross it. You cannot plan travel across something until you know what that something looks like. The Milky Way is classified as a barred spiral galaxy. This phrase combines two critical features. The spiral element refers to the graceful arms that curl outward from the center, sweeping in long arcs that are often regions of active starbirth. The barred element refers to the bright, elongated structure that cuts straight through the middle, a thick bar of stars stretching across the galactic core. Astronomers were not certain that our galaxy was barred until the late 20th century because from our position inside the disk, we cannot easily look at the center from an overhead perspective. It required careful, combined observations tracking the motions of stars, using infrared surveys to peer through dust, and mapping hydrogen gas using radio signals to finally reveal that the middle of our galaxy is not merely a round central bulge, but a distinct, barred one. The full structure consists of several key parts. At the very center lies the galactic bulge. This is a densely packed zone of older stars, shaped somewhat like a peanut when viewed from the side, extending both above and below the main disk plane. Within this bulge is the supermassive black hole known as Sagittarius, a star, which contains about 4 million times the mass of our Sunday. Surrounding the bulge is the bar itself, the elongated collection of stars that actively channels material inward and likely plays a major role in shaping the spiral arms. Extending from the ends of that bar are the arms themselves. The Milky Way has several spiral arms, though they are not rigid or perfectly defined lines. They are best described as density waves regions of higher concentration, where stars and gas crowd together. Our solar system lies in a smaller branch called the Orion Arm, tucked between two larger arms named Perseus and Sagittarius. The main disk of the galaxy is where the majority of visible stars are located. It is incredibly thin relative to its massive diameter, measuring only about 1,000 light-years from top to bottom in the main star-filled layer. If you were to imagine the galaxy as a colossal pancake, the disk is that wide, thin spread of matter. Above and below the disk is the halo, a more spherical region where ancient stars, globular clusters, and dark matter reside. The halo extends far beyond the visible arms, enveloping the galaxy in a vast cocoon. Though we cannot see the dark matter directly, its gravitational pull is measured through the precise motions of stars, and it accounts for most of the galaxy's total mass. Astronomers often study other external galaxies, like the Andromeda Galaxy, our nearest large neighbor, and another barred spiral, to piece together a mental picture of our own. We cannot fly far enough away to take a photograph of the Milky Way's overall shape. Instead, we combine indirect evidence and observations from missions like the European Space Agency's Gaia satellite, which has measured the positions and motions of over 1 billion stars. One key discovery from Gaia is that the disk of the Milky Way is not perfectly flat. It is warped and twisted, likely due to gravitational interactions with nearby satellite galaxies and uneven mass distribution. The pancake analogy, while helpful, is misleading. The disk ripples like a bent plate, a constant reminder that galaxies are dynamic, living systems rather than rigid objects. Understanding this shape is fundamental because it directly impacts how we think about travel. A straight line across the galaxy would pass through different environments: the dense central bulge, the sparse outer edges, or the active star-forming arms. The halo, for instance, is diffuse, ancient, and ghostly, holding onto relics of the galaxy's past. The shape also narrates the galaxy's history. Spiral galaxies form from clouds of gas collapsing under gravity, flattening into disks as they rotate. The bar likely developed as a natural instability in the rotating disk. The spiral arms are not permanent features, but density waves that move around the disk like traffic jams, creating temporary patterns where stars cluster. To describe the Milky Way's shape is to describe something in constant, perpetual motion. Every star, including our sun, orbits the center, taking hundreds of millions of years to complete one circuit. Our solar system lies about 27,000 light-years from the galactic center, orbiting at a speed of roughly 230 kilometers per second. At that pace, it takes approximately 230 million years to complete a single orbit. This means that during the age of the dinosaurs, Earth was in a very different part of the galaxy than it is today. Over our planet's history, the solar system has made about 20 such orbits. When we ask how long it would take to cross the galaxy, the answer depends heavily on the dimension we choose. Crossing through the thin thickness of the disk, from top to bottom, would require only about 1,000 light-years, a small fraction of the 100,000 needed to cross the diameter. Crossing the halo would be much larger still, perhaps several 100,000 light-years. This variation reinforces that our home is not a tidy circle. It is a sprawling, irregular system whose boundaries fade gradually. The galaxy's gravitational influence reaches far outward, holding onto satellite dwarf galaxies like the Magellanic Clouds, which tug at and distort the Milky Way's shape. Furthermore, the shape we describe now is only temporary. In the distant future, the Milky Way will merge with the Andromeda Galaxy, reshaping entirely. Thinking about this structure also focuses us on the places we know best: the Orion Arm, our small spur, contains the Sun, Earth, and everything we know. The nearby Orion Nebula is a vast star-forming region only about 1,300 light-years away. To cross the Milky Way would be to pass through landscapes of stars, each arm with its own distinct character, density, and history. The shape of our home is not just an astronomical curiosity, it is the context for our lives. To imagine its form is to realize we belong to something vast and structured, something that possesses order, even if it is far too large for us to ever cross. That realization, while humbling, is also grounding. We know exactly where we live, even if we will never walk its full boundaries. When we attempt to imagine what it means to cross our galaxy, we must inevitably start with the one traveler that has no rival: light. Light is the fastest thing in the universe, the single benchmark against which all other journeys are measured. Before we consider spacecraft, intergenerational human crews, or drawing board technologies, it helps to understand what light itself achieves, because it is the first and most fundamental traveler across space. Light moves at 300,000 kilometers per second in a vacuum. In a single second, a beam of light can circle the Earth more than 7 times. Over the course of a year, those fleeting seconds accumulate into a distance of nearly 10 trillion kilometers, the distance astronomers call a light year. When we state the Milky Way is 100,000 light years across, we are truly saying that even this tireless traveler, racing at the cosmic speed limit, would need 100,000 years to get from one edge of our galaxy to the other. To fully grasp how remarkable this is, consider the span of human history. 100,000 years ago, Homo sapiens had only just begun to spread beyond Africa. Written language, agriculture, cities, and science were all still tens of thousands of years in the future. In other words, if a single photon had set out from one side of the galaxy back then, it would only just now be completing its journey on the other side. The entire recorded history of our species fits inside just a small fraction of a galactic crossing made at the speed of light. When we look up at the night sky, we are constantly seeing the direct result of this long travel time. The starlight that reaches our eyes is not current, but old, sometimes very old. The sun's light takes about 8 minutes to arrive at Earth. The nearest star system beyond our own, Alpha Centauri, is a little more than 4 light years away. Its light takes 4 years to reach us. So when you look at it through a telescope, you are literally looking into the past, seeing the star as it was 4 years ago, rather than as it is right now. For stars across the galaxy, the time lag can extend to hundreds or thousands of years. This simple fact fundamentally changes the way we think about travel. Light doesn't only move across space, it carries information with it. Every star you observe is sending you a message that began its journey long before you were born. The galaxy is filled with these messengers, each on its way for tens of thousands of years. If you could ride along with one, you would witness a journey longer than the rise and fall of civilizations. It is this benchmark that makes crossing the galaxy such a daunting task. If even light requires that long, then anything slower becomes essentially unimaginable in the context of a human lifespan. The fastest spacecraft we've ever built would take hundreds of millions of years. Even theoretical speeds approaching a significant fraction of light still leave us with time spans far longer than our species has existed. The comparison drives home just how massive our home truly is. When astronomers map the galaxy, they use light as their primary probe. Radio waves, infrared, visible light, and other parts of the electromagnetic spectrum all move at that same universal speed. By collecting these, we build our picture of the Milky Way. In a crucial sense, every observation we make is already a kind of journey. Instead of traveling ourselves, we wait for the light to do the work. Telescopes become our ships, and photons are the explorers. Consider the central black hole, Sagittarius A star. It lies 27,000 light years away. When scientists announce they are observing it, they mean they are studying light and radio waves that originally left the region 27,000 years ago, around the time humans on Earth were still using stone tools. If the black hole were to suddenly change today, we would not know for another 27,000 years. The distance fundamentally delays the news. Light is fast, but even at its speed, the galaxy is large enough to impose long silences. This delay also applies directly to the idea of communication across the galaxy. If another civilization existed on the far side and sent us a signal, that message would take 100,000 years to arrive. By the time we formulated and sent an answer, another 100,000 years would pass. A full exchange, a question, and a reply would span 200,000 years. The implication is clear. Communication across a galaxy is not like conversation across a table. It is more akin to carving words into stone and throwing them into a river that flows for millennia before reaching another shore. The thought of light as the first traveler inevitably leads us to consider relativity. According to Albert Einstein's theory, nothing with mass can reach or exceed the speed of light. It is not merely fast, it is the ultimate, non-negotiable limit. As any object accelerates closer to that speed, its energy requirements rise without bound, and time itself begins to slow relative to an outside observer. The rules of the universe establish light as the unattainable standard, a ceiling that cannot be broken. This means when we use light as our yardstick, we are examining the absolute best-case scenario. No ship, no matter how advanced, can ever quite equal it. And yet, it is important to remember that even light faces challenges. It moves in straight lines unless bent by gravity. Dust and gas can absorb or scatter it over vast distances, blurring the clarity of its message. The light from distant stars is stretched as it passes through the expanding space between them. So, while it is the fastest traveler, it is not invulnerable. Its journey carries the marks of what it has passed through, like footprints left on an impossibly long road. When we discuss crossing the galaxy, we often imagine ourselves following the path light takes. If it requires 100,000 years, then anything slower must, by necessity, take much longer. But there is also something deeply comforting in this thought. We may never travel those distances physically, but the light already does. Every night, photons that began their trip long before human history finally end their journey in our eyes. We are, in a profound sense, already connected to the entire galaxy. This connection is established not by the travel of our bodies, but by the relentless, constant travel of light. To hold on to this idea is to see the Milky Way differently. It is not just a structure we live inside, but a brilliant web of light in perpetual motion, a constant stream of messengers arriving after epic journeys. And as we consider what comes next, how fast we can move, how long our machines take, what limits we truly face, it is essential to remember that light has already shown us the way. It sets the scale, it defines the possible, and it will always arrive first, no matter what paths or technologies we ultimately imagine. When we begin thinking about how long it would take to cross the galaxy, it is easy to leap straight to the grand numbers: light years, millions of years, impossible spans of distance. But sometimes the best way to understand the vastness is to start closer to home with the journey we are already taking. Every second of every day, we are moving alongside the sun as it travels through the galaxy. Our planet is not fixed in space. It is part of a system that actively orbits the center of the Milky Way. In a very real sense, we are already passengers on a colossal, ongoing voyage, one that has been underway since Earth first formed more than 4 billion years ago. The sun, like every other star in the galaxy, follows a path shaped by gravity. The enormous central mass of the Milky Way pulls on it, and the collective influence of billions of stars, dark matter, and gas defines its motion. At this very moment, the sun is approximately 27,000 light years from the galactic center. It moves around that center at roughly 230 kilometers per second, or about 800,000 kilometers per hour. To us here on Earth, those speeds are entirely invisible. We do not feel the motion. The night sky appears calm, and the constellations seem fixed. But over longer time scales, the sun's movement becomes clear. Stars shift their positions relative to one another. The solar system as a whole traces a vast orbit around the heart of the galaxy. That orbit is far from quick. At its current speed, the sun requires around 230 million years to complete a single revolution. In other words, the last time the solar system was in its current position in the galaxy, the Earth looked profoundly different. It was the middle of the Triassic period, long before the first dinosaurs had even evolved. Mammals did not exist. Flowering plants had not yet appeared. The continents were fused into the supercontinent Pangaea. Since then, the solar system has made only about 20 trips around the galactic center. Each lap is so long that it dramatically outlasts entire geological eras on Earth. Thinking about this background orbit helps put our place into perspective. When we ask how long it would take to cross the galaxy, we might imagine building a ship and charting a specific course. But in another sense, we are already on that course. Our star is carrying us along a path that we cannot steer or stop. We are being swept around on a journey that will eventually bring us through different arms, past different star clusters, and under skies that will slowly but certainly shift. The galaxy is not static, and neither are we. As the sun orbits, it does not follow a perfectly circular track. Its path wobbles slightly, moving up and down through the galactic plane. About every 30 million years or so, the solar system drifts either above or below the midline of the disk. This three-dimensional weaving motion means we are not simply circling the center in a flat loop. We are traveling through a complex, weaving landscape carried by the sun's momentum. One way to picture this journey is to scale it down. Imagine the galaxy as a vast city 100 kilometers across. On that scale, the solar system would be a tiny car driving around the outskirts at a steady speed. It would take that car hundreds of thousands of years to circle the city once. This metaphor helps illustrate the central point. We live in a system where even ordinary motion, the background drift of a star, operates on timescales that profoundly dwarf human experience. The sun's orbit also reminds us that the galaxy is not empty. Along our path, we pass through regions of varying density. Sometimes the solar system comes closer to spiral arms where star formation is more active. Sometimes it drifts into quieter regions. Over millions of years, These changes may subtly affect the amount of cosmic radiation Earth receives, or the frequency with which we encounter passing clouds of gas. As passengers on the sun's journey, we are shielded by its magnetic field, which extends outward in a protective bubble called the heliosphere. The heliosphere acts like a protective cocoon, deflecting some of the charged particles that stream through the galaxy. As the solar system moves, the shape of the heliosphere shifts, responding to the conditions of the interstellar medium it passes through. In this sense, the sun is like a vast ship plowing through a sea of particles, and Earth is a protected cabin inside that ship. Another way to consider walking beside the sun is by examining the sheer distances it covers. At 230 kilometers per second, the sun travels more than 7 billion kilometers relative to the galactic center in a single year. Over the course of a human lifetime, that adds up to trillions of kilometers. None of us will live to see even a small fraction of one full orbit. Instead, we each ride along for a brief, short stretch. Our individual lives are tiny chapters inside a voyage that has been underway for billions of years and will continue for billions more. This perspective profoundly changes how we think about crossing the galaxy. We often imagine it as a future endeavor, something we might attempt with advanced technology. But the truth is, the crossing is already happening. We are already in motion, already covering ground. It is simply that the scales are so vast and our lives so brief that we do not notice the progress. From our point of view, the stars appear steady. From the galaxy's point of view, we are part of a restless current flowing outward and around. It is also important to note that the sun's path is not fixed forever. It is influenced by gravitational encounters with other stars and concentrations of dark matter. The galaxy is not a smooth, empty disk, but a crowded environment. Over long timescales, these gravitational nudges gently alter the sun's course. So, while we calculate the sun's orbit as a clean circle taking 230 million years, in reality, it is a winding route, subtly perturbed again and again. When we ask how long it would take to cross the galaxy, we might imagine drawing a straight line from one side to the other. But stars like the sun demonstrate that in practice, there is no straight line. The paths are curved, bent by gravity, and shaped by constant interaction. Walking beside the sun means following a route that is defined by the collective pull of everything around us. It is not a straight highway, but a winding trail, and we move along it whether we choose to or not. This massive motion is also our connection to the rest of the galaxy. Our sun's orbit is not just a background fact. It is part of the key data that helps reveal the hidden mass of the universe. So when we think about crossing the galaxy, perhaps we should start here, with the journey we are already on. The sun is our ship. The Earth is a cabin on board. Every day we ride along as it carves its immense path around the center of the Milky Way. We may dream of faster ships, but in truth, we are already part of a voyage far larger than any human plan. When our minds turn to the ultimate speed required for crossing the galaxy, we invariably arrive at the same benchmark, the speed of light. It is the fastest traveler allowed by the universe, the yardstick against which every other attempt at motion must be compared. To talk about riding on beams of light is to imagine joining that flow, considering what it would mean to experience the galaxy as photons do to cover ground in the most direct way nature permits. The speed of light is about 300,000 kilometers per second. In human terms, it is so fast that ordinary scales become useless. Light travels from the Earth to the Moon in just over 1 second. It can cross the orbit of the Earth, around the Sun, in about 8 minutes. To reach Pluto takes approximately 5.5 hours. To reach the nearest star system, Alpha Centauri, takes a little more than 4 years. These numbers, though still manageable, already begin to drift outside human lifetimes. Once we extend to galactic scales, the time requirements quickly become enormous. Crossing the full diameter of the galaxy at this maximum possible pace still takes 100,000 years. If you were to imagine yourself somehow attached to a photon, the reality grows even stranger. According to Albert Einstein's theory of relativity, from the perspective of light itself, no time passes at all. A photon leaves a star and arrives at its destination without experiencing the duration of the journey. For the photon, emission and absorption happen in the same immediate instant. But for us, moving slowly by comparison, the journey stretches across tens of thousands of years. Riding on beams of light is therefore not just a thought experiment about maximum velocity. It is a thought experiment about time itself. To move at that pace is to remove yourself entirely from the flow of time as we understand it. The closer an object with mass gets to the speed of light, the more its time slows relative to an outside observer, and its mass effectively increases, requiring an infinite amount of energy to keep accelerating. That is why no particle with mass can ever achieve it. Light remains a unique, massless case, able to travel at that ultimate limit. So when we picture riding on beams of light, we are picturing something that cannot happen for us, but that does happen constantly for photons all around us. Every second, light is leaving stars, crossing space, and arriving at new destinations, carrying with it vital information about its origin. When you look up at the night sky, you are looking at light that has been riding toward you for years, centuries, or millennia. Each photon has been in motion all that time, unaffected by age, carrying its message until it finally reaches your eye. If we could truly ride along, the entire galaxy would become a compressed landscape. For astronomers, this property of light is the foundation of their work. Telescopes are essentially devices that collect photons. Every image is a record of light that began its trip long ago. In this way, beams of light are already our explorers. They ride across the galaxy without ships, without fuel, and without rest. They move from star to star, from cloud to cloud, eventually reaching Earth, where we interpret them. If we imagine building technology that could move us at even a fraction of light speed, the timescales shift dramatically. At 10% the speed of light, a journey across the galaxy would take a staggering 1 million years. At half the speed of light, it would still require 200,000 years. Even these reduced time spans remain enormous compared to the lifespan of human civilization. This contrast shows how powerful the benchmark of light is. It sets the ultimate floor on travel time, a figure no amount of technology can undercut. It also shows precisely why so many concepts in science fiction revolve around mechanisms to overcome the light barrier. To make the idea clearer, let's walk through the progression again. A spaceship traveling at the speed of the Parker Solar Probe, 700,000 kilometers per hour, requires more than 600 million years to cross the galaxy. Upgrade that ship to 1/10 the speed of light, and the journey shortens to about 1 million years. Push it to half the speed of light, and it drops to 200,000 years. At the full speed of light, the journey takes 100,000 years. The progression is stark. The closer you approach the speed of light, the more the galaxy begins to look crossable, though always at time scales longer than individual human lives. But the idea of riding on beams of light also connects directly to energy and propulsion. To accelerate even a small object to near light speed requires truly colossal amounts of energy. This is why practical discussions of interstellar travel often focus on propulsion methods that use light itself. Concepts like solar sails or laser propulsion rely on harnessing photons to push a craft forward. In these designs, the craft is not riding on beams of light metaphorically. It is literally being carried by their momentum, pushed across the void by streams of photons. Projects such as Breakthrough Starshot envision tiny probes accelerated to a fraction of light speed by powerful ground-based lasers. If successful, they could reach nearby stars within decades rather than millennia. Even here, though, the galaxy as a whole remains daunting. A probe moving at 1/5 the speed of light would still need 500,000 years to cross. The numbers remind us that while light is fast, the distances are immensely vast. And the combination keeps the dream of galactic crossings firmly in the realm of imagination. Still, there is something profound about thinking in these terms. To picture ourselves riding on beams of light is to step outside our usual scale. We live our lives in minutes and hours, counting days and years. Light ignores these divisions, leaping across the solar system in minutes and across the galaxy in millennia. It is the universal traveler, moving always at the same pace, unaffected by who is watching. By imagining ourselves alongside it, we gain essential perspective. We see our own slowness, our own limits, but also our deep connection to the cosmos. Because light does more than move. It illuminates every single detail we know about the galaxy. From the shape of its arms to the presence of its black hole, all knowledge comes from light. By collecting it, by riding along in thought, we effectively turn photons into knowledge. And that knowledge, though it may never shorten the journey time, brings the galaxy closer to us in a different intellectual sense. So, as we continue to wonder how long it would take to cross our galaxy, it is vital to hold on to the image of beams of light already making that trip. They leave stars, travel across the void, and eventually reach us. We may never ride them in reality, but in a way, we already do. Every time we look up, every time a telescope collects a faint signal, every time starlight falls onto Earth after a journey of thousands of years, the galaxy reveals its immense scale. But beams of light are always in motion, always crossing, and always arriving. And in their journeys, we find both the limits and the possibilities of our own. When we step away from the benchmark of light speed and look back at the machines we have actually constructed, the contrast is stark. Light is the ultimate traveler, the standard that defines the fastest possible speed. But our spacecraft, the real ships humanity has placed into the void, move at a radically different pace. Compared to photons, they are crawling. And yet, for us, they represent the pinnacle of engineering, the clearest evidence of our ability to reach beyond Earth. To accurately understand how long it would take to cross the galaxy, we cannot ignore this reality. We must reckon with the slow march of current spacecraft technology. The fastest human-made object so far is the Parker Solar Probe. Launched in 2018, it was designed to study the sun's outer atmosphere. To achieve its mission, it had to dive deep into the sun's gravity well, and in doing so, it was accelerated to speeds greater than any previous spacecraft. At its peak, The Parker Solar Probe moves at about 700,000 kilometers per hour. That is nearly 200 kilometers every single second, an extraordinary velocity by human standards. To us, it is unimaginably fast, and yet, in galactic terms, it is virtually motionless. At 700,000 kilometers per hour, crossing the Milky Way's diameter of 100,000 light-years would take more than 600 million years. That figure is so enormous, it overshadows almost everything else we know. For context, the age of the dinosaurs ended approximately 65 million years ago. You would need to multiply that span by nearly 10, and you still would not reach the time required for a single crossing at Parker Solar Probe speed. The Earth itself is only about 4.5 billion years old, meaning a crossing at that pace would consume a significant fraction of the entire lifetime of our planet. Consider another example. Voyager 1, launched in 1977, it has now traveled beyond the sun's heliosphere into interstellar space. It is moving at around 61,000 kilometers per hour relative to the Sunday. This is much slower than the Parker Solar Probe, but it remains one of the fastest spacecraft ever built and holds the record for the farthest distance from Earth achieved by a human-made object. At Voyager 1 speed, the time to cross the galaxy would stretch into 1.5 billion years. This number is even more difficult to imagine. It means that if Voyager 1 had been launched at the dawn of the Earth itself, it would still be far from completing its journey across the Milky Way today. When we frame things this way, the slow march of our spacecraft becomes an unavoidable reality. Our machines are remarkable engineering achievements, but they operate on scales that make galactic crossings functionally impossible. We send them to nearby planets, to the outer reaches of the solar system, and in the case of the Voyagers, into the space between stars, but none of them are designed for journeys across the entire galaxy. Their lifespans are measured in decades, their power sources are severely limited, and their speeds are tiny compared to what is required. This reality does not make them less impressive. Voyager 1 and Voyager 2 carry golden records, photographed discs embedded with sounds and images of Earth. They are small messages in bottles cast into the ocean of space, but those bottles drift slowly. In the time it takes Voyager 1 to move a single light year, thousands of years will pass on Earth. That is the slow march of spacecraft. Why are they so slow? The answer comes down to energy. Reaching high speeds requires enormous amounts of energy. Rockets are fundamentally limited in how much fuel they can carry and how efficiently they can burn it. The Parker Solar Probe reached its record speed not by firing engines endlessly, but by skillfully using the sun's gravity to accelerate as it fell closer and closer. Voyager 1 used gravity assist from Jupiter and Saturn to slingshot outward at higher speeds than rockets alone could provide. These methods allow us to cheat a little, using celestial mechanics to gain velocity, but they still fall far short of the pace needed to traverse the galaxy in meaningful timeframes. Another key limitation is endurance. Even if a spacecraft could be accelerated to higher speeds, it would need to survive for hundreds of thousands or even millions of years to complete the journey. Electronics degrade, power sources run out, and collisions with tiny particles of dust at high velocity could be catastrophic. The galaxy is not empty, and traveling at a fraction of light speed through interstellar space poses dangers that are trivial at slower speeds, but deadly when scaled up. Our current spacecraft are simply not built for those conditions. They are designed for missions lasting decades at most, not geological ages. And yet, the slow march is highly instructive. It shows us the stark difference between imagination and engineering. On one side, we picture beams of light, photons racing across the galaxy in 100,000 years. On the other, we look at our actual machines crawling so slowly that billions of years would not suffice. The gap between these two extremes is the gap between what physics allows in principle and what technology permits in practice. To cross that gap, we would need breakthroughs far beyond what we currently know. But the slow march also offers hope. Each spacecraft we launch is faster and more ambitious than the one before. The Parker Solar Probe is faster than Voyager, which was faster than the missions before it. Future concepts like nuclear propulsion, fusion drives, or solar sails could, in theory, accelerate craft to significant fractions of light speed. They remain speculative, but they represent concrete steps toward narrowing the gap. The march may be slow now, but it is not motionless. This slow pace gives us perspective on time. We often think of human history as long, stretching back thousands of years, but against the backdrop of galactic travel times, it is merely an instant. The spacecraft we have launched so far will not cross the galaxy. They will not even cross a significant fraction of it, but they do represent the first footsteps, the initial attempts to move beyond our immediate neighborhood. They are small, but they matter because they demonstrate that motion beyond Earth is possible. If the slow march continues, if each generation builds faster ships, then eventually the pace could increase, perhaps not to light speed, but to significant fractions of it. At that point, the galaxy would still take hundreds of thousands of years to cross, but the dream would come significantly closer to reality. The slow march is not only a description of spacecraft moving through space, it is a description of humanity's progress, step by step, experiment by experiment, moving from the possible to the previously impossible. For now, however, the numbers remain fixed. Parker Solar Probe, 600 million years. Voyager 1, 1.5 billion years. These are the scales of time we are dealing with when we talk about actual machines we have launched. It is sobering, but also motivating, because it shows us exactly how far we have to go and how much room there is left for discovery. If light is too fast to reach and our current probes are too slow, what lies in between? What technologies could bridge the gap? What new methods of propulsion might turn the slow march into something quicker, if not immediate? Whenever the subject of crossing the galaxy arises, the conversation inevitably turns toward limits. We can easily imagine faster spacecraft, stronger engines, and future breakthroughs. But there is one fundamental boundary in nature that refuses to budge. That is, the speed of light. Physics tells us that nothing with mass can move faster than light through space. This restriction is not just a technical problem awaiting a solution. It is a fundamental, non-negotiable feature of the universe. Understanding it is critical if we want to know what crossing the Milky Way really means, because this speed limit sets the outer boundary for every possible journey. The number itself is straightforward, about 300,000 kilometers per second. In 1 second, a beam of light can travel around the Earth 7 times. In 1 minute, it can travel 18 million kilometers. In a year, nearly 10 trillion kilometers. These figures define the light year, the distance light covers in 12 months. When astronomers state the galaxy is 100,000 light years across, they are saying it is 100,000 times that immense distance. That is already staggering. But the real challenge lies not in the size of the distance, but in the physical impossibility of exceeding the speed of light. Albert Einstein's theory of relativity explains why. As an object with mass accelerates closer to the speed of light, its energy requirements grow exponentially. The faster it goes, the more energy it takes to increase its speed even slightly. At everyday velocities, this effect is invisible, but at a significant fraction of light speed, the effect becomes dominant. To reach 90% of light speed would require enormous amounts of energy. To reach 99.9%, the energy demand skyrockets, and to actually reach the speed of light itself would require an infinite amount of energy, a physical impossibility. That is precisely why the speed of light is not just very fast, but the absolute, ultimate barrier. This is not merely a mathematical trick. It has been confirmed repeatedly in experiments. Particles in accelerators can be pushed to speeds very close to light, such as 99.999% of that speed. But no matter how much energy is added, they never reach 100%. The universe simply does not allow it. Photons, being massless, are the only things that can travel at that exact, ultimate pace. Everything else must remain strictly below it. For galactic travel, this restriction carries enormous implications. Even if we built engines capable of pushing ships to incredible velocities, we could never match the pace of light. We could get close, but never all the way. That means that the lower bound on a galactic crossing is permanently set in stone. 100,000 years is the absolute minimum, and that minimum is for a traveler that has no mass at all. For us, with mass and limited energy, the trip would always take longer. This limit also brings time into the conversation in strange ways. As an object approaches light speed, time dilation occurs. From the perspective of an outside observer, the traveler's clock ticks more slowly. A ship moving at 90% of light speed might experience only half the time that passes for someone at rest. At 99.9%, the difference is even more dramatic. For the crew on board, the trip might feel shorter, though from the outside, centuries or millennia still pass. This phenomenon is often described as a loophole, but it does not break the rule. The speed of light remains uncrossable. The effect simply shifts the way time is experienced. This means that any realistic ship would still take far longer than a human lifespan in the eyes of Earth, even if the passengers themselves felt otherwise. The speed limit of the universe also fundamentally governs communication. No message can move faster than light. Radio signals, laser beams, and any other form of electromagnetic transmission all obey the same law. That means the fastest way to send information across the galaxy still takes 100,000 years from edge to edge. This fact alone explains why interstellar communication is so challenging. If another civilization exists far away, we would be speaking to one another across gulfs of time measured in millennia. A single exchange would take longer than the rise and fall of multiple human civilizations. On Earth, a speed limit can be overcome by changing the technology. A better engine, a stronger design, and the limit is broken. With light, that is not the case. No technology can ever overcome it. It is not a practical obstacle, but a fundamental one. The laws of nature themselves forbid faster travel. This has led to great speculation. Science fiction often imagines ways around the speed limit concepts like warp drives, wormholes, or hyperspace are attempts to cheat the rule by creating shortcuts that bypass the distance. Physicists have studied some of these ideas seriously, such as the Alcubierre warp drive, which involves compressing space in front of a ship and expanding it behind. In principle, this could allow effective, faster-than-light travel without technically violating relativity, but the energy requirements are enormous, far beyond anything we can currently produce. For now, these remain highly speculative ideas, so the speed limit remains intact. We live in a universe where light defines the fastest possible pace. That boundary shapes every single question we ask about galactic travel. Without it, the journey would be a simple matter of building better engines. With it, the journey becomes a matter of rethinking what is genuinely possible. At the same time, this absolute limit provides stability. If signals could outrun light, causality itself would break down. The order of cause and effect could be scrambled. The speed limit preserves the consistency of time. It is not just a barrier, but a framework that makes physics work. For our purposes, though, it demands humility. When we imagine crossing the galaxy, we must remember that the fastest possible traveler still requires 100,000 years. Every spacecraft we build and every propulsion system we dream up must exist within that frame. The speed limit of the universe is not a suggestion, it is the law. And yet, even with this constraint, there is still room for wonder. Time dilation offers strange possibilities. Theoretical propulsion concepts might one day approach significant fractions of light speed. Communication across the galaxy, though slow, is not impossible in principle. The limit sets the rules, but it does not erase the game. We can still imagine journeys, still calculate times, and still wonder what it would mean to move through the arms of the Milky Way. That is the power of this boundary. It is absolute, but it also defines the canvas on which imagination can play. And every time we look up, every time a telescope collects a faint signal, every time starlight falls onto Earth after a journey of thousands of years, the galaxy reveals its immense scale. Beams of light are always in motion, always crossing, and always arriving. And in their journeys, we find both the limits and the possibilities of our own. When we talk about crossing the galaxy, the first and most critical piece of information is its actual size. It might seem simple enough to state the Milky Way is about 100,000 light-years wide, but that figure hides centuries of immense difficulty, trial, error, and the slow accumulation of human knowledge. Measuring the galaxy from our vantage point inside it is one of the hardest problems in astronomy. We lack the luxury of stepping outside to take a photograph from above. Every single detail we learn has to be gathered from within, pieced together, like trying to map a dense forest while standing among the trees, with clouds of dust and darkness blocking much of the view. The history of measuring the Milky Way stretches back long before modern science. Ancient cultures noticed the hazy band across the night sky, giving it names rooted in myth. To the Greeks, it was the milk spilled from the breast of a goddess, which gave the galaxy its modern name. To the Chinese, it was the Silver River. These early descriptions were not scientific measurements, but they reflected an ancient recognition of the Milky Way as something distinct and vast. Serious attempts to measure the galaxy began in the 18th and 19th centuries. One of the first notable efforts was by William Herschel, who, with his sister Carolyn, conducted detailed star counts. Herschel assumed that if he counted stars in every direction, regions with more stars must correspond to the thicker parts of the galaxy. Using this method, he correctly deduced that the Milky Way was a flattened disk, but incorrectly placed the sun near the center. Dust clouds obscured his view, making star counts unreliable in certain crucial directions. His map was a bold first step, but incomplete. Later, in the early 20th century, new techniques revolutionized the process. Astronomer Henrietta Leavitt discovered a relationship between the brightness and period of certain variable stars known as Cepheid variables. This breakthrough allowed astronomers to measure distances to stars far beyond the limited reach of parallax, which had been the only reliable method before. By studying Cepheids, astronomers like Harlow Shapley determined that the galaxy was far larger than previously thought, tens of thousands of light-years across, and, crucially, that the sun was not at the center, but offset, located in one of the spiral arms. This discovery represented a profound shift in perspective, moving humanity from a central position to a more modest one within the cosmos. As technology advanced, so did the accuracy of these measurements. Radio astronomy allowed scientists to look through the dust that blocks visible light. Neutral hydrogen gas emits radiation at a wavelength of 21 centimeters, and by mapping this emission across the sky, astronomers could finally trace the spiral arms of the galaxy. This provided the first clear evidence of the Milky Way's structure as a barred spiral, with arms winding out from the center. Infrared telescopes added more detail, since infrared light penetrates dust better than visible light. In recent years, the European Space Agency's Gaia mission, launched in 2013, has fundamentally revolutionized the process. Gaia has measured the positions and motions of more than 1 billion stars with extraordinary precision. These data points form a three-dimensional map of the galaxy, showing not only where stars are, but how they are moving. This has allowed astronomers to refine estimates of the galaxy's size, shape, and mass, and to uncover features like the warp in the disk and streams of stars left behind by smaller, merging galaxies. Gaia's results largely confirm that the visible disk is about 100,000 light-years across, though its halo of dark matter and old stars extends much farther, possibly 200,000 or even 300,000 light-years. Measuring the galaxy is not just about size, it is also about mass. By studying the rotation curve of stars, how fast they orbit the galactic center at different distances, astronomers discovered that the visible matter alone cannot account for the observed motions. Stars far from the center move faster than expected, which implies the presence of additional unseen mass. This is the crucial evidence for dark matter, a mysterious substance that does not emit or absorb light, but exerts gravity. Estimates suggest that dark matter makes up the vast majority of the Milky Way's mass, enveloping it in a colossal halo. Without it, the galaxy's rotation would not hold together. So, when we measure the Milky Way, we are measuring not only what we see, but also what we cannot see. These efforts show how much complex work is hidden behind the simple phrase, 100,000 light-years. It is a number built from centuries of observation, from the first star counts to the most modern space telescopes. For us, these numbers set the scale. When we say the galaxy is 100,000 light-years wide, we are saying that crossing it would take light itself 100,000 years, and any spacecraft much, much longer. That measurement provides the essential framework for all our questions about interstellar travel. It shows us not only the galaxy's size, but our modest position within it. The Sun lies about 27,000 light-years from the center, orbiting quietly in a small spur between larger arms. Measurement is the key that unlocks this understanding, transforming a mere blur in the sky into a structured, knowable place. With the measurement of the galaxy now firmly in hand, we can return to the ultimate thought experiment regarding speed. If we let ourselves imagine the ultimate shortcut for travel, it would be to do exactly what light already does. Light is the fastest traveler in the universe, moving at 300,000 kilometers per second. If there were a way to truly ride along with it, every single journey would be utterly transformed. To hitchhike on a photon is impossible in reality because photons have no mass and, crucially, experience no time. But thinking about what it would mean gives us a sense of scale that numbers alone cannot provide. It allows us to picture the galaxy not as a slow, impossible distance, but as a path light already crosses constantly and effortlessly. Suppose, for the sake of this thought experiment, that you could magically attach yourself to a photon, leaving a star on one side of the Milky Way. In the first instant, you would leave your star behind. If you began near our sun, the first 8 minutes would carry you to Earth's orbit. In just over 4 hours, you would have reached Neptune. In a single day, you would have left the solar system entirely, surpassing the distance of Voyager 1, humanity's most distant probe. What takes us decades of effort, light achieves in less than 1 day. From there, the milestones would come quickly. In a little over 4 years, you would pass Alpha Centauri, the nearest star system. Sirius, the brightest star in Earth's night sky, would pass after about 9 years. Stars we know well from constellations would fall behind within decades. Hitchhiking on a photon shows how even the nearest stars, which seem impossibly far with our current technology, are crossed with ease by light. But the real test comes when you aim not for nearby stars, but across the entire 100,000 light years of the Milky Way. Even at the speed of light, the trip still requires 100,000 years. That means leaving behind every moment of recorded human history. If a photon set out from one side when the first humans began painting on cave walls, it would still only be partway through the disk today. The photon's journey forces us to accept the overwhelming scale of the galaxy, because it shows us that even at the fastest possible speed, the trip is beyond the scope of anything we know. And yet, photons are making this journey all the time. Every star is constantly releasing light in every direction. Some of these photons reach Earth, striking our atmosphere, our telescopes, or our eyes. Each photon that arrives carries with it the history of its journey. To hitchhike on one would be to see the galaxy as a series of arrivals, each new place reached in the blink of an eye for light. But in centuries or millennia for us, astronomers, in a sense, already hitchhike on photons. Every observation they make is based on collecting light that has been traveling for years or longer. When we image the galactic center, we are seeing light that began its trip 27,000 years ago. To do astronomy is to wait patiently for photons to arrive, effectively riding them backwards through time to the place they began. This is the closest we can come to hitchhiking on light in reality, and it is how we know what we know about the Milky Way. If you could truly ride a photon, you would also experience the galaxy differently in terms of perspective. Distances would collapse. The separation between arms, which spans tens of thousands of light years, would vanish in what feels like an instant. Entire star systems would flash by. From this unique vantage point, the galaxy would seem small, almost compressed, because the limits of time are gone. That profound contrast with our slow, heavy, massive world is what makes the thought experiment so powerful. It shows us both how vast the galaxy is and how quick light can be. The inherent limits of this thought experiment also highlight why light is so central to our understanding of space. Everything we know about galaxies, nebulae, black holes, and stars comes from photons. They are the only carriers of information across the void. To ride one would be to live inside the act of observation itself. There is also a sobering lesson here. If the fastest possible traveler still requires 100,000 years to cross the Milky Way, then any slower traveler is destined to spend far longer. Hitchhiking on a photon shows us the best case, the absolute lower limit of speed. From there, we can only move downward. Our spacecraft may take millions or billions of years. Even speculative engines operating at significant fractions of light speed require hundreds of thousands of years. The photon's journey is the cleanest, most direct path, and it clearly shows us why galactic travel is so difficult to imagine for beings who live for less than a century. And yet, the act of imagining it remains valuable. It stretches our sense of time. It reminds us that the galaxy is not just a backdrop, but a place full of journeys already happening, carried by light. Photons are crossing the Milky Way constantly. We are surrounded by them, illuminated by them, and informed by them. To think of hitchhiking on a photon is to step into the stream of the cosmos, to see how the fastest traveler makes the impossible journey look routine. When we return from this thought experiment to our own pace, the contrast can feel humbling, but it also gives us a sense of belonging. Even if we cannot ride photons ourselves, we are bathed in their journeys. They reach us from across the galaxy and beyond, and through them, we know where we are. They are our messengers, our explorers, our hitchhiking partners, whether we notice them or not. And with them as guides, we can continue thinking about what it would mean for us, bound to mass and limited engines, to move across the Milky Way in our own slower way. When we talk about crossing the galaxy, the first and most critical piece of information is its size. Stating the Milky Way is about 100,000 light-years wide hides centuries of astronomical difficulty. Measuring the galaxy from our vantage point inside it is one of the hardest problems in science, requiring us to piece together a map from within, much like mapping a forest while standing among the trees. The history of this measurement began with early observations of the hazy band across the sky, which ancient cultures named with myths like the Silver River. Serious attempts started in the 18th century with William Herschel, who conducted star counts and correctly deduced the galaxy was a flattened disk, though he incorrectly placed the sun at the center due to obscuring dust. Later, in the early 20th century, new techniques revolutionized the process. Astronomer Henrietta Leavitt discovered the relationship between the brightness and period of Cepheid variables, which allowed astronomers like Harlow Shapley to measure vast distances. Shapley found the galaxy was far larger than previously thought, and, crucially, that the sun was offset, located in one of the spiral arms. As technology progressed, radio, astronomy, and infrared telescopes allowed us to look through the cosmic dust, mapping the emission of neutral hydrogen gas at a wavelength of 21 centimeters, provided the first clear evidence of the Milky Way's structure as a barred spiral. In recent years, the European Space Agency's Gaia mission has measured the positions and motions of more than 1 billion stars with extraordinary precision, confirming that the visible disk is about 100,000 light-years across. Measurement is also about mass. By studying the rotation curve of stars, astronomers discovered that the visible matter alone cannot account for the observed motions. This provides the crucial evidence for dark matter, a mysterious substance that makes up the vast majority of the Milky Way's mass, enveloping it in a colossal halo that extends far beyond the visible disk. For us, the number 100,000 light-years provides the essential framework. It tells us that crossing it would take light itself 100,000 years, and any spacecraft much, much longer. It is a reminder of our modest position. The sun lies about 27,000 light-years from the center, orbiting quietly in a small spur between larger arms. Measurement transforms a simple blur in the sky into a structured, knowable place. When we look back at the machines we have actually built, the contrast with light's speed is stark. Our spacecraft are crawling, yet they represent the pinnacle of engineering. To understand the reality of the crossing, we must reckon with the slow march of these machines. The fastest human-made object so far is the Parker Solar Probe, which moves at speeds up to 700,000 kilometers per hour by using the sun's gravity. Even at this extraordinary pace, crossing the Milky Way's diameter would take more than 600 million years. Consider Voyager 1, launched in 1977. It has traveled beyond the sun's heliosphere into true interstellar space, moving at about 61,000 kilometers per hour. While this speed is impressive, to cover a single light year, Voyager 1 needs more than 17,000 years. To cross the entire galaxy, it would take about 1.5 billion years. This means that if Voyager 1 had been launched at the dawn of the Earth itself, it would still be far from completing its journey today. The Voyagers were never designed to cross the galaxy. Their mission was planetary exploration. They are small messages in bottles, carrying the golden record with sounds and images of Earth, a symbolic gesture of humanity's existence. In the time it takes Voyager 1 to move a single light year, thousands of years pass on Earth. Their slow march shows the enormous gap between what physics allows, 100,000 years, and what engineering permits, in practice, 1.5 billion years. They live in that gap, demonstrating that the problem of galactic travel is fundamentally one of energy and endurance. Our machines are not built to survive the hundreds of thousands or millions of years required for even fractional galactic progress. Yet, the Voyagers are inspiring. They are the first wave of explorers, tiny and fragile, but persistent. Their continuing signals, traveling across billions of kilometers, remind us that distance is not absolute and that progress begins with small, determined steps. Without them, the concept of leaving the solar system would still be only a dream. With them, it is a fact. Since no single human life could ever experience a galactic crossing, the idea of interstellar travel must transform. It becomes a question not of individual lives, but of generations. This is the concept of a generation ship. If a voyage is going to take thousands or tens of thousands of years, the crew must become a self-sustaining society. The ship must be built to support life indefinitely, with the destination reached not by the people who set out, but by their distant descendants. Even at a theoretical speed of 1/10 the speed of light, crossing the Milky Way would still require 1 million years. Even to reach a nearby star 100 light years away would take 1,000 years. On such journeys, the voyage itself is the home. People would be born, live their lives, and die within the contained interior of the ship, passing on the responsibility and the mission as a historical legacy. This raises profound questions about continuity. How would motivation, knowledge, and culture be sustained over thousands of years? The people who began the journey would know the goal, but after many generations, the purpose might fade, replaced by the immediate realities of life aboard the ship. The belief is that the journey would eventually become the culture itself, a foundational myth that defines their society. The technical requirements are staggering: indefinite recycling of air, water, and food, energy sources that last for millennia, and shielding against radiation and psychological strain. The problem of crossing the galaxy is not only distance and speed, it is continuity. Human institutions struggle to last even centuries. To succeed, we would need not only new technology, but new ways of thinking and new philosophies about purpose. If we apply this to a full galactic crossing, the timescales become utterly overwhelming. At 1/10 light speed, 1 million years means tens of thousands of generations. Entire species evolve in less time. To imagine a generation ship making that crossing is to imagine the creation of an entirely new civilization. The journey would not leave us unchanged. It would profoundly reshape who we are, transforming the descendants into entirely new forms of life and society by the time they arrive. The concept of a generation ship is compelling because it forces us to think in terms of a chain that stretches far beyond our lifetimes. It asks us whether we can sustain purpose across millennia. Light makes the crossing in 100,000 years. Spacecraft crawl along for billions. The generation ship is the idea that human perseverance, spanning vast epochs, might one day bridge the gap between these extremes. It shows us how much the galaxy demands of us if we ever hope to cross it. The only way for beings like us to approach the task of galactic crossing is to stretch our perspective to accept that we cannot do it alone. It would take not just lifetimes, but entire civilizations. Generations would be the currency of such a voyage. When the vastness of the galaxy feels overwhelming, it is natural to wonder whether the universe might allow some kind of shortcut. If light speed is the absolute limit, and even a photon requires 100,000 years to make the crossing, then perhaps there is another way. This is where the speculative ideas of warp drives and wormholes enter the discussion. They are not technologies we can build today, and they may never be, but they demonstrate how far human imagination can stretch when confronted with impossible distances. They also highlight the difference between what the laws of physics say is forbidden and what they leave open as theoretical possibilities. A warp drive, in its most familiar form, is an idea proposed by physicist Miguel Alcubierre in the 1990s. Building on Einstein's equations of general relativity, Alcubierre showed that it was mathematically possible to create a bubble of space-time that contracts in front of a ship and simultaneously expands behind it. The ship itself would sit inside the bubble, remaining technically motionless relative to the space immediately surrounding it. But because space itself is shifting, the bubble could move faster than light relative to distant observers. This would not violate relativity, because the ship would never locally exceed light speed. Instead, the fabric of space-time itself would carry the ship forward. The concept is fascinating, but the problems are enormous, requiring vast amounts of energy and, critically, exotic matter with negative energy density, things that have never been observed in sufficient quantities. Wormholes offer a different kind of shortcut. Also rooted in general relativity, they are solutions to Einstein's equations that theoretically connect two distant points in space-time through a tunnel. A traveler could enter one mouth of the wormhole and instantly emerge from the other, no matter how far apart the two entrances are in ordinary space. The core idea is that space itself is folded so that the distance is shortened. Like warp drives, wormholes are extremely unstable. To keep one open long enough for anything to pass through would also require exotic matter with negative energy density. Even if tiny wormholes exist at quantum scales, stabilizing them and scaling them up remains far beyond our current capabilities. The dreams of warp drives and wormholes persist because they offer a way out of the time trap. They promise travel not limited by distance, but by geometry. If space can be bent or folded, the galactic crossing could potentially be made in years instead of millennia. Although the engineering seems impossible, the fact that Einstein's equations allow for these solutions, at least mathematically, keeps the conceptual door open. These ideas serve as thought experiments that push the very limits of what we can conceive. It is important to note that these shortcuts are not without complications. They raise profound questions about causality and time travel. A warp bubble or an unstable wormhole could, under certain conditions, allow for paths through space-time that loop back on themselves, creating the possibility of arriving before you left. This is why many physicists suspect that nature has mechanisms to prevent such structures from forming or persisting. Stephen Hawking even proposed a chronology protection conjecture, suggesting that the laws of physics fundamentally forbid time machines. From the perspective of crossing the galaxy, warp drives and wormholes represent a powerful form of conceptual hope. They suggest that maybe the universe leaves a loophole, even if that loophole requires physics we do not yet understand. The act of looking for this loophole forces us to study relativity, quantum mechanics, and cosmology more deeply, pushing science forward. They remind us that the galaxy is not only vast, but also embedded in a flexible fabric of space-time that is far stranger than our daily experience suggests. They allow us to talk about crossing the Milky Way, not in billions of years, but in moments. When people first hear that the galaxy is 100,000 light years across, and that even at the speed of light, the journey would take 100,000 years, the idea of crossing the Milky Way seems completely out of reach. But relativity complicates this picture. It introduces a twist that makes the question less straightforward: time dilation. The closer you travel to the speed of light, the more time slows down for you relative to someone who remains at rest. This is a core concept of Einstein's theory of special relativity, published in 1905. Since the speed of light must be constant for all observers, time and space must adjust to maintain that constancy. The faster you move, the slower your clock ticks relative to someone standing still. This effect is not a trick. It has been repeatedly measured with high-precision atomic clocks on fast-moving planes and satellites. Applied to galactic travel, this means that even if the trip seems impossibly long from Earth's perspective, it could seem much shorter to the traveler. Suppose a spacecraft could reach 99.9% of the speed of light. From Earth's point of view, the time to cross the galaxy would still be over 100,000 years. But for the people on board, the effect of time dilation would be so extreme that the journey might take only a few centuries or even decades of their subjective time. This is the puzzle. The same journey has two different answers depending on where you measure from. From Earth's perspective, no one can cross the galaxy in a human lifetime. From the traveler's perspective, it might be entirely possible. Both answers are correct within the framework of relativity, because time itself is not absolute. It depends on motion. A famous way of illustrating this is the twin paradox. If one twin stays on Earth while the other travels close to light speed, the traveling twin experiences time more slowly. When they return, the Earth-bound twin has aged decades or centuries, while the traveler has aged only a few years. The traveling twin would indeed return younger, applied to a galactic crossing. This means the crew of a near light-speed ship could, in principle, make the trip and feel only a fraction of the time pass, while vast ages would slip by on Earth. This creates a fascinating scenario where time dilation offers a loophole for the traveler. They could reach distant parts of the Milky Way within their subjective lifetime. However, relativity does not remove all obstacles. The energy required to reach such speeds is immense, and collisions with interstellar dust would be catastrophic. Furthermore, time dilation severs the connection with the world they left behind. The price of the shortcut is that the rest of humanity moves on without them. The crew becomes exiles in time, separated not only by space, but by centuries or millennia of history. When they look back, they see a world that no longer exists. This is why time dilation is a puzzle, not just a curiosity. It shows us how different the universe is from our daily intuition. We think of time as universal, but relativity shows it bends and stretches with motion. The galaxy reveals this truth on scales too large to ignore. To ask how long it takes to cross is ultimately to ask, whose clock are you using? The answer is not one number, but two. Both are true, and they do not match. Time dilation offers possibilities but also raises profound challenges. It shows us that the rules of the universe are more flexible than we might think, but also that those rules come with severe consequences. Any attempt to cross the galaxy will be shaped not only by where we go, but by how time itself will treat us along the way. When people imagine traveling across the galaxy, the primary obstacles that come to mind are usually distance, time, and speed. But if you consider carefully what lies between one side of the Milky Way and the other, there are fundamental hazards that must also be considered. Among the most dramatic hazards are black holes. These strange objects are scattered throughout our galaxy, some small, some massive, some hidden in darkness, and one truly enormous at the very center. If you were to draw a path across the Milky Way, sooner or later you would pass near some of them, and their presence would undoubtedly shape the journey. A black hole is a region where gravity is so strong that nothing, not even light, can escape. This concept comes directly from Albert Einstein's general relativity, which shows that mass severely curves space-time. When enough mass is concentrated into a small volume, the curvature becomes so extreme that it creates an event horizon, a boundary beyond which escape is physically impossible. To an outside observer, this region is invisible, as no light comes out. All that can be seen is the influence on nearby stars, gas, and dust. In our galaxy, the largest black hole is Sagittarius A star, located at the center, about 27,000 light-years from Earth. It contains approximately 4 million times the mass of the Sun, packed into a region smaller than our own solar system. Its existence was definitively confirmed by tracking the orbits of stars that whip around the center at incredible speeds, pulled by the immense, unseen mass. The Nobel Prize in Physics in 2020 was awarded for this pioneering work. If you were crossing the Milky Way, this central black hole would be one of the most important landmarks, an immense gravitational anchor around which the entire galaxy orbits. But Sagittarius A star is not the only one. Stellar mass black holes, formed when massive stars collapse at the end of their lives, are scattered throughout the disk. Astronomers estimate there may be millions of them in the Milky Way. Most are invisible because they do not emit light unless they are actively consuming gas from a companion star. When they do, they produce powerful X-rays that allow us to detect them. Otherwise, they are silent, hidden, detectable only by their subtle gravitational effects. This makes them both fascinating and potentially hazardous to any imagined journey. Suppose you were traveling across the galaxy in a ship. The odds of directly colliding with a black hole are vanishingly small because they are not large targets. But passing too near one could have dramatic effects. Its gravity could alter your trajectory, slingshotting you onto a new path or pulling you inward to destruction. Even without crossing the event horizon, the tidal forces near a black hole can be immense, pulling objects apart in a process sometimes called spaghettification. For travelers, black holes are not only hazards, but also potential tools. Just as Voyager 1 used the gravity of Jupiter and Saturn to gain speed, a ship might in principle use the gravity of a black hole for a slingshot maneuver. Approaching at the right angle and distance, the ship could gain velocity from the black hole's immense pull without falling in. This would be extremely dangerous, requiring precision far beyond our current technology. But in theory, the same gravity that threatens destruction could also offer assistance. From Earth, we study black holes not by visiting them, but by observing their effects. The Event Horizon Telescope, a global network of radio telescopes, produced the first direct image of a black hole shadow in 2019. These observations confirm that black holes are real, physical distortions of space and time. Knowing they exist and where they are is crucial to mapping any imagined crossing of the galaxy. Surveys suggest there could be around 100 million stellar mass black holes in the Milky Way. The chance of encountering one on a straight path is tiny, but their sheer number ensures that any crossing would pass relatively near several of them. Imagining black holes along the road gives the galaxy texture. It is a landscape dotted with these silent giants, reminding us that the galaxy is a place of creation and destruction, where the rules of physics grow stranger the closer you get to them. For a traveler, planning a course would mean not only calculating distances and speeds, but also mapping where these hazards lie, staying far enough away to avoid their pull, yet aware that their presence cannot be ignored. If you imagine trying to cross the Milky Way, one of the first questions that arises is how you would know where to go. The galaxy is not a simple stretch of road with signs along the way. It is an ocean of stars, hundreds of billions of them, each shining with its own light. In that sense, the only map available to any traveler is the light those stars send out. Every photon that reaches us is not only illumination, but also critical information. Learning how to read that information is learning how to navigate, and realizing that starlight itself is the guidebook for crossing the galaxy. On Earth, navigation has always relied on light. Before compasses or global positioning systems, sailors steered their ships by the sun during the day and the stars at night. The same principle applies to the galaxy, only on a much larger scale. Starlight carries the clues about where we are and where we are going. The key lies in the fact that starlight is not uniform. Every star has its own spectrum, a fingerprint of lines that reveals its composition, temperature, and motion. When light from a star is spread into a spectrum, the lines shift depending on motion. If a star is moving toward us, its light is compressed, shifting toward the blue. If it is moving away, the lines shift toward the red. This Doppler effect allows astronomers to measure velocities with great precision. In this way, starlight becomes a record not only of what a star is, but also of how it moves. Distances, too, can be drawn from light. Nearby stars can be measured using parallax, the tiny shift in their apparent position as Earth orbits the Sunday. For more distant stars, astronomers use standard candles, objects whose intrinsic brightness is known. Cepheid variables, with their predictable relationship between brightness and pulsation, are prime examples. By comparing how bright they appear to how bright they should be, astronomers calculate their distances. Starlight, in other words, contains the ruler as well as the compass. This is how the shape of the Milky Way has been uncovered. By collecting light from countless stars, astronomers piece together their positions and motions, revealing the spiral arms, clusters, and central bulge. The Gaia mission has taken this to extraordinary levels, measuring the positions and movements of more than 1 billion stars with incredible accuracy. Its data forms a living map of the galaxy, showing not only where stars are now, but where they are moving in the future. This is exactly the kind of map any traveler would need. If you were aboard a ship trying to cross the galaxy, you would have no signs, no roads, and no landmarks except starlight. But that would be enough. By measuring the spectrum, brightness, and position of stars around you, you could triangulate your place. The stars themselves are the coordinates. Each photon carries the data needed to find your way. The usefulness of starlight extends beyond visible light. Infrared, ultraviolet, radio, and X-rays all carry additional information. Infrared penetrates dust, revealing hidden stars. Radio waves trace cold gas, showing the arms of the galaxy, such as the emission from neutral hydrogen gas at a wavelength of 21 centimeters. X-rays point to extreme objects, like neutron stars and black holes. Each wavelength is a different layer of the map. Starlight can also serve as a clock. Pulsars, the rapidly rotating remnants of massive stars, emit beams of radiation at extremely regular intervals. These pulses are so precise that they rival atomic clocks. A network of pulsars could function as a galactic GPS, allowing ships to locate themselves anywhere in the Milky Way. By measuring the timing of the signals, the galaxy provides its own beacons. All we have to do is learn to read them. The usefulness of starlight is its abundance. Even if dust clouds obscure visible light, infrared and radio bypass the dust, even if stars vary, careful observation over time accounts for variability. Starlight is not perfect, but its abundance makes it reliable. Thinking of starlight as a map also reshapes how we view the journey itself. It reminds us that the galaxy is not a void, but a field of markers. Each star is a point on the chart. Even the dark gaps where few stars shine are information. They tell us where the dust is thickest. For those who dream of galactic journeys, this is an essential lesson. The first step is not speed. The first step is orientation, knowing where you are going, and how to tell the difference. Starlight provides that foundation. It is the map drawn not by human hands, but by the universe itself, available to anyone who can read its code. With that, the road across the Milky Way is no longer an empty stretch of time and space. It is a route with markers, signposts, and coordinates, all written in light. And every night when we look up, we are reading it. When we look up at the Milky Way on a clear night, we often think of it as crowded. The band of light across the sky gives the impression of stars packed together, a glowing ribbon of countless suns. But the reality is very different. For every star we see, there are vast stretches of emptiness between them. If you were traveling across the galaxy, this emptiness would be what you encountered most of the time. The stars themselves would be rare, scattered islands in a sea of space. Between the stars stretches the silence. This environment is so empty that words like desert or void hardly capture it. The average distance between stars in our part of the Milky Way is about 4 light years. That means that if you set out from the sun and traveled in a straight line, you would typically need to go 4 light years before you came close to another star like it. Light covers that distance in 4 years. Voyager 1, our most distant spacecraft, moving at more than 61,000 kilometers per hour, would need over 70,000 years. For a human traveler, the gap between stars is a barrier as daunting as the galaxy itself. What makes the silence between stars so striking is not just the physical emptiness, but the absence of signals. The universe is filled with background radiation, the afterglow of the Big Bang, the faint hiss of energy left over from the birth of the cosmos. But the kind of signals we associate with life, with civilization, are missing. Radio telescopes scan the sky, searching for artificial transmissions, but so far none have been confirmed. The galaxy is not only empty of matter between stars, it is also empty of voices. The silence is literal. For travelers, this silence would be a constant companion. Imagine a ship moving through interstellar space. The stars would be distant points of light, but most of the view would be darkness. Communication with Earth, if possible at all, would take years or centuries, depending on the distance. Each step forward would take the ship deeper into isolation. The silence would be more than a lack of sound. It would be the absence of contact, the absence of reassurance that anyone else is near. The emptiness between stars is not absolute. There are particles drifting in interstellar space, mostly hydrogen atoms. There are occasional clouds of gas and dust, and there are cosmic rays, high-energy particles zipping through space. But compared to the density of matter on Earth, a cubic centimeter of air contains about 10 billion trillion molecules. A cubic centimeter of interstellar space may contain just one atom. Traveling through it would feel like passing through a vacuum. And yet, this near vacuum is not irrelevant. Over thousands of years, the sparse atoms of the interstellar medium would still exert a drag on a fast-moving ship. Dust grains, though tiny, would strike with enormous energy at near-light speeds, creating dangerous impacts. Shielding would be necessary, not because space is crowded, but because even rare collisions at high velocity are catastrophic. The silence is not safe. It hides risks that are invisible but real. From another perspective, the silence between stars is also an opportunity. It is what makes the stars themselves so distinct. In the middle of emptiness, each star becomes a beacon. The contrast between the silence and the signal is what allows navigation. Without the silence, the signals would blur together. The emptiness gives structure to the galaxy, separating the islands of light so that they can be seen, studied, and understood. The silence also forces us to think about time differently. On Earth, we are used to short communication delays, but with the stars, the delays stretch into years. A message sent to Alpha Centauri would take 4.3 years to arrive, and another 4.3 years for the reply. That is nearly a decade for a single exchange. Across the galaxy, the silence becomes permanent. Messages take tens of thousands of years to cross. For practical purposes, there is no conversation possible. The silence is baked into the structure of space-time. The mental adjustment required to live with such silence would be profound. The galaxy is often described as a desert, but unlike deserts on Earth, the spaces between stars are not home to plants, animals, or civilizations. They are dark, cold, and silent. For any journey across the Milky Way, most of the time would be spent not near stars, but in this silence. The destinations may be bright, but the road is quiet. The silence does not mean absence of meaning. It means room for meaning. It means that when signals do arrive, they matter. It means that when stars appear, they shine all the brighter against the void. The silence is not an obstacle to crossing the galaxy, but the medium through which the crossing takes place. To understand the Milky Way, we must understand not only the stars, but also the long stretches where nothing speaks and nothing moves except at the slow pace of drifting atoms. When we think about journeys, we usually measure them in times that fit within our lives. The Milky Way does not fit into those scales. The galaxy forces us to stretch our perspective until it almost breaks, because the simple truth is that crossing it takes forever compared to anything we know. Start with the speed of light. Nothing moves faster. It is the limit set by the universe itself. At that speed, a crossing from one side of the disk to the other still takes 100,000 years. That figure alone is beyond anything familiar. 100,000 years requires a chain of 1,000 human lifetimes. Whole civilizations rise and fall in much shorter times. To cross the galaxy at light speed would require surviving a timescale longer than all of recorded human history. Now, slow down to the speeds we can actually achieve. Voyager 1, the fastest probe traveling away from Earth, would need 1.5 billion years to cross the galaxy, about 1/3 the age of Earth itself. The Parker Solar Probe would still need more than 600 million years. These are times so long they erase any hope of continuity. Even more ambitious proposals, like ships that might theoretically reach 1/10 the speed of light, still yield enormous times. The crossing would take 1 million years. The numbers never shrink into manageable scales. They remain stubbornly vast. The galactic crossing takes so long, primarily due to 3 unyielding constraints. First is geometry and speed. The Milky Way's disk stretches an observed 100,000 light-years across, creating distances so immense that even light itself appears sluggish, requiring 100,000 years to complete the journey. Our fundamental human limitation prevents us from even approaching this speed limit, as our current engines are too weak and our energy reserves are too small. Furthermore, as speed increases, the risks from radiation and collisions with sparse interstellar matter grow catastrophic. Second is endurance and engineering. A ship with mass must accelerate gradually, stretching the journey time, but more critically, no known machine or biological system is designed to last for the required time frame of hundreds of thousands of years. Metals corrode, electronics fail, and power sources decay, making the challenge of simply keeping a vessel functioning dwarf any engineering we currently know. Finally, the human factor complicates the voyage profoundly. Since individual humans live for less than a century, carrying people across the galaxy requires a commitment spanning generation after generation, introducing psychological and societal complexities on an unprecedented scale to sustain the mission over millennia. The galaxy is too large for individuals to comprehend as a journey. To us, it takes forever, because forever is the only word that captures time so far beyond our direct experience. Time dilation complicates the picture, but does not erase it. From the perspective of a traveler moving close to light speed, the journey may seem shorter. A crew might experience only decades, while centuries pass outside. But time dilation does not eliminate the objective time scale of the crossing. For the galaxy as a whole, it still takes 100,000 years at best. Time dilation simply divides the forever into different perspectives. The crossing remains unreachably long from Earth, but becomes possible for the traveler at the cost of being disconnected from everything left behind. The silence between stars contributes as well. Even if a ship could move fast enough, communication lags grow unbearable. A message to Earth from halfway across the galaxy would take 50,000 years to arrive. The crossing is not just long in time, it is long in isolation. The reason crossing takes forever is that forever is the scale of the galaxy itself. The Milky Way operates on timescales we can barely imagine. Our lives are short, and our technologies are primitive compared to what would be needed. That is why crossing feels unreachable. Yet, in another sense, forever does not mean impossible. Light makes the trip constantly. The galaxy functions as a whole, even though its components are so far apart. The question is not whether the journey is infinite, but whether we are finite. And this understanding leads naturally into other questions. If crossing takes forever, perhaps our role is not to move across the galaxy in ships, but to comprehend it in its own terms, to read it through starlight and model it through telescopes. Perhaps the galaxy is not meant to be crossed in our terms, but to be understood in its own. The following content serves as the final segment of the podcast episode, continuing the discussion on galactic travel, challenges, and theoretical limits. The content adheres to the length constraint of $10,000, $12,000 characters and maintains the required documentary tone. When the scale of the Milky Way feels overwhelming, it is natural to wonder if there might be a way to cheat the system. If light itself requires 100,000 years to make the crossing, and if even the boldest designs for fusion or antimatter engines still yield travel times of hundreds of thousands of years, then the mind begins searching for a shortcut. Humanity has always done this. Faced with a mountain, we look for a pass. Faced with an ocean, we look for currents. Faced with the galaxy, we begin to imagine paths that bend or fold space itself, routes that might take us where speed cannot. The most famous shortcut is the wormhole. General relativity allows for solutions in which two distant points in space-time are connected by a tunnel. Enter one end, emerge at the other, skipping the intervening distance. The idea is often illustrated by folding a sheet of paper so that 2 points touch, then poking a hole between them. To cross normally requires moving along the surface. To cross through the hole requires almost no distance at all. Applied to the galaxy, a wormhole could reduce a journey of 100,000 light years to a single step. The mathematics for wormholes is straightforward enough, but the physical reality is another matter. Wormholes, if they exist, would be unstable. They would collapse before anything could pass through unless they were held open by exotic matter with negative energy density. No such matter has been found in usable amounts. Even if it exists, controlling it on galactic scales would require technology far beyond anything we can currently imagine. Still, the possibility remains in theory, and that makes wormholes the archetypal galactic shortcut. They represent the hope that distance is not absolute, and that geometry itself can provide an escape from forever. Another imagined shortcut is the warp drive. Instead of moving through space faster than light, the ship manipulates the space around it, contracting the region ahead and expanding the region behind. The ship itself remains motionless inside a bubble of normal space, but the bubble itself moves. This idea, first proposed by Miguel Alcubierre in the 1990s, shows that general relativity permits such a distortion. The problem, once again, is energy. The amount required is astronomical, far beyond what stars themselves produce, and it requires exotic forms of matter not known to exist. But as a shortcut, it illustrates another path, not through a tunnel, but through the manipulation of the medium itself. Beyond these, there are other speculative ideas. Some involve using the fabric of space in ways we do not yet understand. Theoretical models suggest that extra dimensions may exist, curled up beyond our perception. If those dimensions could be accessed, they might allow shortcuts through higher dimensional space, rendering galactic distances irrelevant. None of these ideas are confirmed. They remain speculative, but they show how imagination stretches when faced with impossible journeys. When we talk about shortcuts, it is easy to dismiss them as science fiction, and in many cases they are. But science fiction has often served as a testing ground for ideas that later became real. That does not mean wormholes or warp drives will ever exist, but it does mean that imagining them has value. It pushes our understanding of physics. It frames the questions we ask. It highlights the difference between what is strictly forbidden by the laws of nature and what is simply beyond our current technological reach. Part of the appeal of shortcuts is psychological. When faced with numbers like 1 million years or 1 billion years, the human mind recoils. A shortcut offers relief. It says, perhaps there is a hidden path that makes the impossible manageable. This is not just a desire for convenience, it is a desire for hope. At the same time, imagining shortcuts helps us understand the structure of the galaxy more deeply. Thinking about wormholes leads to studies of space-time geometry. Thinking about warp drives leads to questions about energy and negative mass. Each shortcut, even if never realized, opens a line of inquiry that enriches science. In this way, shortcuts are not escapes from knowledge, but powerful tools for gaining it. When people first hear that the galaxy is 100,000 light years across, and that the journey would take 100,000 years even at the speed of light, the idea of crossing the Milky Way seems completely out of reach. But relativity introduces a twist that makes the question less straightforward: time dilation. The closer you travel to the speed of light, the more time slows down for you relative to someone who remains at rest. This is a central prediction of Einstein's theory of special relativity. If light speed is constant, then time and space must adjust to preserve that constancy. The faster you move, the slower your clock ticks relative to someone standing still. This effect has been measured many times with high-precision atomic clocks and spacecraft. Applied to galactic travel, this means that even if the trip seems impossibly long from Earth's perspective, it could seem much shorter to the traveler. Suppose a spacecraft could reach 99.9% of the speed of light. From Earth's point of view, the time to cross the galaxy would still be over 100,000 years. But for the people on board, the journey might take only a few centuries or even decades of their subjective time due to the extreme time dilation. This is the puzzle. The same journey has two different answers depending on where you measure from. From Earth's perspective, no one can cross the galaxy in a human lifetime. From the traveler's perspective, it might be possible. Both answers are correct within relativity, because time itself is not absolute. It depends on motion. The twin paradox illustrates this clearly. A twin who travels close to light speed would experience time more slowly, returning home to find that their earthbound twin has aged decades or centuries, while the traveler has aged only a few years. Applied to a galactic crossing, this means the crew of a near light-speed ship could, in principle, reach the far side of the galaxy and feel only a fraction of the time pass. However, relativity does not remove all practical obstacles. The energy required to reach such speeds is immense. Furthermore, time dilation severs the connection with the world they left behind. The crew becomes exiles in time, separated not only by space, but by centuries or millennia of history. When they look back, they see a world that no longer exists. This dual perspective raises fascinating implications for crossing the galaxy. On one hand, time dilation offers a loophole for the traveler to achieve a subjectively short journey. On the other hand, it makes communication with Earth nearly impossible. A message to Earth from halfway across the galaxy would take 50,000 years to arrive, and the reply would take just as long. The crew would be cut off, not only physically, but temporally. The galaxy reveals this truth on scales too large to ignore. To ask how long it takes to cross is ultimately to ask whose clock you are using. The answer is not one number, but two. Both are true, and they do not match. Time dilation shows us that the rules of the universe are more flexible than we might think, but also that those rules come with immense consequences. After following the scale of the Milky Way across distances and times that strain the imagination, it helps to pause and return to the one place we actually know. All of the calculations, the questions about speed, the speculations about shortcuts, and the visions of future ships begin from a single reference point: here. The sun lies about 27,000 light-years from the center of the Milky Way, positioned in a quiet spur between two larger arms. It is in the middle ground, where orbits are stable and conditions allow for planets like Earth. This location is sometimes described as the galactic habitable zone. From this position, the dream of crossing the galaxy may seem distant, but the act of understanding it is already remarkable. Without leaving home, without traveling even beyond the solar system, humanity has measured the distances to stars, mapped the arms of the disk, detected black holes at the center, and traced the halo of dark matter that surrounds everything. All of this knowledge has been gathered by studying light that arrives here on Earth. In that sense, the journey across the Milky Way has already begun, not physically, but intellectually. We are travelers of knowledge long before we are travelers of distance. That perspective also reminds us why the galaxy feels so large. We measure it from our scale, from lives that last less than a century, from civilizations that rarely endure more than a few thousand years. Against that backdrop, 100,000 years at light speed looks impossible. Billions of years at spacecraft speeds look like forever. But the journey is only long because we are small. That realization does not make the road shorter, but it helps us understand why it feels endless. Back at home, the questions become more practical. Instead of asking how to cross the entire galaxy, we can ask how to send probes to the closest star systems, how to build telescopes that reveal more detail. The Voyagers are already part of that extension. They are not crossing the galaxy, but they are leaving the solar system, moving slowly outward into interstellar space. Their journeys remind us that every step counts, even small ones. From here at home, we can measure, plan, and imagine. The galaxy is vast, but it is not unknowable. The more we observe, the more the details emerge. What was once only a glowing band in the sky becomes a dynamic spiral with billions of suns, and through that knowledge, the galaxy becomes less an abstraction and more a place we belong to, even if we never cross it. The galaxy is not just a background, it is an environment, and we occupy a specific position within it. This contrast, the vastness out there against the familiarity here, does not diminish the galaxy. It makes it more meaningful. It shows that in the middle of immensity, small worlds can exist, where life flourishes, where thought arises, and where questions about journeys across the galaxy can even be asked. As we imagine crossing the Milky Way, it is easy to feel insignificant, but returning to home reveals the opposite. It is precisely because we are small and brief that the galaxy feels so large. The fact that we can even measure it, describe it, and imagine traveling across it is extraordinary. The road may be endless, but the act of seeing it is itself a journey. And so, the crossing of the galaxy remains a dream, but one rooted in real knowledge. The intellectual journey continues every day here at home. That journey is what makes the galaxy real to us.